Hello students, welcome to the next lecture on the linear algebra. Today we will discuss about these linear span and the linear combinations. Myself Dr. Garg, work in the School of Mathematics, Thapar Institute, India. What is the content of this video is we will discuss about the concept behind the linear combination, span and the smallest subspace with respect to their illustrative examples. So we discuss about the 10 examples in this video so that you can easily understand these concepts. What is a linear combination is if you take any of the vector space V and their elements as a Vi, then every elements of the V, any of the elements of V apart from this, say this element, it can be written like a linear combinations of here. What is the meaning of that? Remember that alpha I is from my field, or you can say these are my scalars are. Your target is to find the values of the alpha I. For example, the first example is how you can write V as a linear combinations of there. It means you have to write as a linear combination. Your target is to find the value of the alpha 1, alpha 2 and alpha 3. If you are able to find these values successfully, then you can say yes, it is a linear combination, otherwise not. So I can substitute the value of the V, V1, V2, V3. If you equate the coefficients, you will get here. And you can easily solve these three equations either with the help of the row reduced, rank or any of the calculator are there. You will get these three values. Since alpha is are you can easily determine, so hence V is a linear combinations of this Vi. Another example is you have to find the condition of the A, B and C so that the matrix E is a linear combination of this. It means it is given that it is written in the form of the linear combination. Your target is to find the value of A, B and C. What is the definition of the linear combination? It means you can write this as a linear. You can substitute the value of the E, you can substitute the value of the A and so on. Now since the two matrices are equal, when it means you have to, your target is to find the value of the alpha 1, alpha 2 and alpha 3. From here you can easily find the value of the alpha 2. From here you can easily find the value of the alpha 1. You can substitute these two values here. You can find the value of the alpha 2 easily. So this is B minus C plus alpha 3. So you can get the alpha 3 as A minus B plus C. Now since there are the four equations, 3 I solved, so I can substitute alpha 1, alpha 2, alpha 3 in here. We will get the required conditions are here. You can get the value of the alpha 1, alpha 2 and alpha 3. I can substitute all these values in this equation. You will get the required solution are there. So since I want the condition, so this is the required condition. Next definition is what is the linear span. If you consider as a subset of the V, which is a non-empty subset of the V, then this set is said to be the linear span if it consists of all those linear combinations of the elements of the S. So remember that the linear combinations is the elements of the V. But here now we can write as a linear span, that is the element of the S. So take the elements of the S, you can see we can take the elements of the S and then write as a linear combinations with this. So if we are able to write them, then we will call as the linear span, which is denoted by L of S. It can be easily proved that this linear span form a vector space, or you can say it form a subspace of the vector space. How you can prove that it's a subspace? If I start with the definition of the linear span, it will be here. In order to prove whether it's a subspace or not, we have to take the two elements from this set and then prove that their linear combination is belong to the same set or not. So start with this one. If I take X and Y belong to the LS, what is the meaning of that? X is in this form. I can say I varies from 1 to N are there. Y, J varies from 1 to M and so on. Here Vi and the Wj belong to the S and this one. Your target is to prove this value. So I can take these two values from the scalar field. These are my F is my field. I can substitute the value of the X here. I can substitute the value of the Y here. So which can be written like this. Now when you can say, if you open this bracket, you will get here. When this element belong to the linear space, linear span, whenever whatever the coefficients of the alpha I, it belongs to the S. You can see V1, V2 up to the Vn belong to the S. S, W1, W2 and Wn, Jm is also belong to the S. Another thing you have to prove that the coefficient of the Vi is in F. You can see lambda belong to the F, alpha I is belong to the F, beta I, J belong to the F. It means this is also belongs to the F are there. So you can see this is a linear combinations of the Vi and the Wj. Hence, this is my subspace. Look at this example are there corresponding to this. You have to determine the subspace which is spanned by the V1 and V2. I consider the set S as a V1 and V2. Then your target is to find the linear combination of this. What is the definition is? That is alpha I Vi. So here I varies from 1 to, in this case it is my 2. I can write this LS as alpha 1 V1, alpha 2 V2 for some scale. I can substitute the value of the V1 and V2 here. If you open this bracket, you can take the pair of the X, Y and Z is the required subspace. Second part, how you can prove that whether this and this elements are belongs to this or not. How you can prove that? That's very simple. I can start with the first part. Your target is to check whether this belongs to the linear span or not. How you can prove that? What is the linear span? That is nothing but the linear combinations. So we can start from here. I can write the linear combination of which is equal to this, and if you are able to find the value of the alpha I successfully, then your answer is yes, otherwise not. So from here you can equate the coefficients. So you can get the value of the alpha 1 is my 1. If you substitute the value of here, you will get alpha 2 is my 1 by 3. If you substitute alpha 1 here, you will get alpha 2 as my -1. But you can see both the value can't be same at can't be get the same values are there. It means this is not possible. Hence, this element does not belong to the linear span. Look about this one. If you equate them, you will get this value, and from here you will get alpha 1 is my 2. If you substitute here, you will get this value, and from here you will get this value. Both are the same values. It means these elements belong to the linear span. What is the smallest subspace are there? If you consider as a non-empty subset S of the V, S is the subset of the V, and here, then any of the subspace W which contains the S is called as the smallest subspace if and only if satisfy the two properties. Number one is S must be the subset of the W. You can see in this definition. If W1 is the any another subspace of the V, whatever the subspace of here, such that W is the part of this W1 and W must contains in the W1. What is the meaning of that? It means S1 will be like here. This is my W1. Then only this condition will be satisfied. So you can see W is the smallest subspace if satisfied these two properties. It is the smallest subspace. It is denoted by either this curly braces or like here. Also, you can easily prove that the linear span, this what is the LS is my linear span, is the smallest subspace among this vector space. So what is the meaning of that? Your target is to prove LS satisfied these two properties. How you can prove that? That's a very simple. You can start with the any of the W is the subspace of the V such that S belongs to S is a subset of W. Now your target is to prove here. How you can prove in terms of the set? So if I take any of the elements in the first part, then after the calculation your target is to prove this belongs to the W also. What is the meaning of that? It means here. So here, this is your target. We can start from here. If V belong to the LS, LS is my linear span, it can be written like here. Now your target is to prove in the W. So since Vi is belongs to the S, but S is a subset of the W, what is the meaning of that? It means Vi is also the part of the W, and W is my subspace. What is the meaning of that? If W is my subspace, then I can written as a linear combination of this alpha I Vi is also the part of the W, because W is my subspace. And what is that? Alpha I Vi is nothing but my V, so V is also belongs to the W. So what is the meaning of that? If I start from here, you will get this value. It means L of S is nothing but my W. So this is the definition for it. Here W1 is nothing but my W. So it means L of S is my smallest subspace of that. Look at that, 8 more examples are there so that you can easily understand it. Check whether this is a linear span generated by this. What is the meaning of the linear span is you have to check whether this is the linear combination of these elements or not. That's very simple. You can write as a linear combinations. If you are able to get the value of the alpha 2, alpha 1 and alpha 3, then your answer is yes. If you are unable to get these values, then your answer will be no. You can equate the coefficients. Once you will equate the coefficient, you will get these results out there. So what you can do is that if you add these two values, Or if you solve these three equations, if you add 1 and 3, you will get this expression. You can see if you add 1 and 3, alpha 2 will be cancelled out. If you add alpha 2 and alpha 3, equation 2 and equation 3, you will get this. Can it be possible? Sum of the alpha 1 and alpha 3 is 3, sum is my 2 by 3. It can never be possible. Hence, this is not belongs to the linear span, because we are unable to find the values of the alpha. Show that the value of this generate. So generate means you have to check whether it can be written as a linear combinations or not. What is the V3 is? V3 is nothing but my R cube, and R is my field. This is my field. This R cube is my vector space. So you can take any of the element in the R cube. So I can take V as any of the element, and your target is to express this as a linear combinations. How you can write as a linear combination? So you can write as a alpha 1, alpha 2, since there are the 3 vectors, so I can write like here. And your target is to find the values of alpha. You can substitute the value here. You can get the values of this one. Can you find the alpha 1? Alpha 1 is nothing but my x. Alpha 2, I can substitute the value here. You can get the value of this value. I can substitute the value of the alpha 1 and alpha 2 here. You can get the value of the alpha 3 here. Now since alpha 1, alpha 2 and alpha 3 are uniquely determined, so therefore I can get each of the elements, whatever the elements of the R cube, it can written like here. You can take as either 1, minus 3 or 7. It means this is my x, this is my y, this is my z. It is belong to the linear span of here. Therefore V1, V2, V3 generates the V3. Check whether the span, that is a linear span of S and the linear span of the T are same or not. This is the target behind that. So how you can prove that? Since this is a set, so you have to say L of S must contain in L of T, and L of T must contain L of S. That's a very simple task out there. What is the S? S is the element of the V1 and V2. Firstly, my target is to write this one. What you can prove that? In order to prove this element, what you can do is you can take every element of the S if it can be written in the form of the LT. Means this is the element of the S. If I able to find it right in terms of LT, these are the elements of the LT, that is a V1, V2, V3. These are the elements of the V1, V2 and V3. Can you find the coefficients here? Can you find this coefficient? You can easily find that this is 1. I can write these values as a 0, or V1, V2, V3 are the values are there. It means every element of the S can be written as the every elements of the T. So we can start from here. You can write as this is a 1, rest all are 0. It means L of S is there. Same for here. Your target is to write every element of the T. So T is my V1, V2 and the V3. I want to express this as elements of the S. S is my V1 and V2. It means I have to write in this form. Can you find this coefficient of the V1, V2 so that it can be written in the form of here? For the first pair, you can easily write that it's a 1 and 0. For the second pair, you can easily write this one. But what about this value? You can't easily write that. It means your target is to find this value. How you find this? This is nothing but the linear combinations. You can write like here. You can substitute the value of the V3, V1 and V2, equate the coefficients. You can see this is 3 alpha 1 plus 3 alpha 2 and so on. Can you solve these two equations? You can easily solve them. From first and the third, you can get the value of alpha 1 and alpha 2 are here. If you substitute this value in here, check whether it's satisfied or not. You can see minus 4, it is minus 6 plus of 2. You can see this is satisfied. It means you can easily determine alpha 1 and alpha 2. Hence, alpha 1 is my minus of 3. This is minus 2. So I can substitute this value as here. So each element of the T, it can be written as an element of the S. It means this satisfied. So from equation number 1, from equation number 2, what you conclude that it is a spanner. Look at the another example are there. In this case, you have to prove that the linear span of this is not equal to the linear span of this. Again, you can take this as my S, this as my T. So it means your target is to prove this is not the same. So how you can prove that? Again, we will follow the same approach. Assume that it can be written like this way. It means if it is a linear span, What is the meaning of the linear span? I can write this as a linear combinations for the field R. I can substitute the value of the V1, V2, V3 and V4, and our target is to find, if you are able to find these values successfully, then we can say yes, it can be the linear span, otherwise not. Now you can equate the coefficient, you will get here. You can easily solve, you can solve from the first and third, you can easily add them. You will get as a 4y is nothing but 7a minus b. So y is 7a minus b upon 4. If you substitute this value in equation number 1, you will get the value of the x and y are here. Now since I solved the equation number 1 and 3, check whether this satisfy equation number 2 or not. I can set the value here. You will see they are not equal to the right hand side. It means you are unable to find the value of the x and y. Hence, these three equations has the no solution. It means it can never be written as the linear combinations. Look at another one is there. So again you have to check whether L of s is t. How you can prove that? Again your target is to check whether this is here. For this you have to start from the s element, that is alpha, beta and gamma. Can you write this in terms of the t, that is alpha, beta, alpha plus beta and beta plus gamma? Can you write this value? Can you write the coefficients of this? You can easily write, since I need a 1, so this is 1, I can write other values are 0. Similarly for the second pair beta, I need these values. This is my alpha plus beta plus this value as of here. So you can see that this value I can 0, I can write this 1, this is 0, this is 0. And for the gamma, how you can write that? This is 1, this is here, this is alpha plus beta and this is my beta plus gamma. So how you can write that? Since I need a gamma, so it means I can write here as 1, but it will take a plus beta also, so I can take this value as minus 1. The rest all the values are 0. What is the meaning of that? L of s is a part of L of t. On the other hand, how you prove that L of t is a part of the L of s? We can start from the t, that is alpha, beta, alpha plus beta, and here. Can you write these values in terms of the s? S is my alpha plus beta plus gamma. Can you find these values? I can write this as a 1, this as a 0, this is 0. Can you write this again? This. Can you write this as 1 alpha, 1 beta, and I can write as a gamma 0. And for here, this is 4 here. So from here, both these values can be written as L of s is L of t. Or you can easily see every element of the t, you can see every element of the t is the linear combinations of the element of the s. So you can write easily as here. And for this part, you can see this. Look at the last example are there. You have to prove that whether this is a polynomial. Check whether this first polynomial lies in the span of this or not. Again, very simple. Assume that firstly it lies in that. If it lies in the s, it means your target is to find here. Again, your target is to find the values of the alpha I. If you are able to find it, then you can say yes, it belongs. Otherwise, it's a no. How you can find the values of the alpha is, you can equate the coefficients of the x cube. You can equate the coefficient of the x square. You can equate the coefficient of the x, and it's a constant. You can easily see that from the equation number 1, you can get alpha is here. Can you find the value of the alpha 2 from here? It is nothing but my 3 minus alpha 3. You can find the value of the alpha 4 for here, 5 minus 2 alpha 3. Substitute alpha 2 and alpha 3 in equation number 3. You can get this as of. Now substitute alpha 2 and alpha 3 here, both are equal. So what is the meaning of that? If you solve them, you will get both the values as here. Once you will get alpha 3 and alpha 4 as a 5 by 3, you can substitute this value here, or here you will get this value as this one. Now alpha 1 is my 0, alpha 2 are here, so all you can easily determine, so it means this lies in the s. How you can do the second part? Again, you can firstly assume that you can try to write in terms of the polynomials. Find the coefficients are there, like of the x cube, this is x square, this is x and the constant. Now you can simply add them. If you add the equation number 3 and 4, what will happen? This is 10, this is 2 alpha 2 plus 2 alpha 3. What is the meaning of that? This is alpha 2 plus alpha 3 is my 5. So if you add the equation 3 and 4, you will get this. But you already know that alpha 2 plus alpha 3 is 3. Is it possible? No. It means you are unable to find the values of the alpha I. Therefore, this does not belong to the S. So this is the way you can solve the problems of the linear span and the combinations. We will see in the next class how you can solve the direct sum of the subspace. Till then, you can simply follow this link for finding the various videos. Best of luck, students. Happy learning.